Like in the classroom, prepare yourself for the lesson ahead. Silently prepare your materials for math. It will be best to have writing materials with you. You may use a notebook or a printout of the Learning Worksheet 1.2. Let us now settle down. Algebraic techniques in determining limits of functions. You have learned from the first lesson what a limit of a function is given table of values and graphs of functions. The limit L of f of x is the real number that f of x or y will approach as x approaches c. This statement is written using this notation, and it is read as the limit of f of x as x approaches c is L. From the discussion and exercises on this definition, did you observe anything in common among the examples you have encountered? Can we generalize from these observations? Consider the following functions. You are given in the graph y equals 3, y equals 0.5, y equals -1, and y equals -5. For each function, you can clearly see from the graphs that y will approach the same value whenever x approaches any value. This means if f of x is any constant k, then the limit of f of x as x approaches c is equal to k, wherein k is the function value f of c. Given the function f of x equals x, we consider this line with y equals c when x is equal to c. Hence, as x approaches a certain value, the y values approach the same value, or the limit of f of x as x approaches c is equal to c. Now, if we look at this line, which is the graph of f of x equals 2/3 x, for any x value, the corresponding y value is simply multiplied by 2/3. So, the limit as x approaches c is 2/3 times c. And for any function f of x equals a constant k times x, then its limit as x approaches c is equal to k times c, which is again the function value f of c. Moving on, the line f of x equals 3x minus 4 can be considered as a sum or difference of functions. Based on the graph, we can easily recognize that the limit of f of x as x approaches a value c is the function value f of c, which is the same as the sum or difference of the functions we mentioned earlier. On the other hand, a function such as f of x equals x squared over 2 may be considered as a product of two functions. In this case, since f of x equals g of x times h of x, and the limit of f of x as x approaches c is g of c times h of c, we can also conclude that the limit of f of x as x approaches c is again the function value f of c. Combining the generalizations we have discussed so far, we can conclude that if f is a polynomial function, then the limit of f of x as x approaches c is f of c, and therefore the limit is determined by substituting the value of x to the equation. As an example, given the polynomial function x cubed plus 12x squared plus 9x minus 2, we may refer to the graph to determine the limit of f of x as x approaches negative 3. Or we may also substitute negative 3 to x in the equation, thus obtaining negative 2. Will this technique be applicable when dealing with a quotient of two functions? If f of x equals g of x over h of x, can we also apply that the limit of f of x as x approaches c is the limit of g of x as x approaches c divided by the limit of h of x as x approaches c? Let f of x be equal to x squared plus 2x minus 3 all over quantity x squared minus 1. Looking at the graph, the limit of f of x as x approaches 0 is 3, since tracing the curve from the left and from the right of 0 both lead to the y value 3. If we take the limits of the numerator and the denominator by substitution, since both are polynomial functions, we will obtain negative 3 over negative 1, which is also equal to positive 3. In this case, the same algebraic technique applies since f has a function value at c. In the graph, we observe that the curve is asymptotic to x equals negative 1. But there is no function value at negative 1. Applying the algebraic technique, we obtain negative 4 over 0, which is undefined. And therefore, there is no such value that y approaches as x approaches negative 1. When x equals 1, substituting this to both the numerator and the denominator leads to a 0 over 0, which is indeterminate. From these examples, we observe that aside from polynomial functions, the quotient of functions with a function value at c will also have a limit as x approaches c, which is equal to f of c. If an undefined value is obtained, like in the previous example, this means that there is no such value that y approaches as x approaches negative 1. In this particular function, the y values approach negative infinity as x approaches negative 1 from the left and approaches positive infinity as x approaches negative 1 from the right. Hence, the limit does not exist. Another possible scenario when dealing with a quotient of two functions is obtaining an indeterminate value. Considering the graph, this results to a whole at the given value of x. Since it is 0 over 0, it means the numerator and the denominator have factors that become 0 given a certain value of x. Given this, we can check what will happen if these factors are cancelled. Will the simplified expression have a function value at c? With the given function, the numerator can be factored into x minus 1 and x plus 3, while the denominator is factored into x minus 1 plus x plus 1. After canceling x minus 1 from the numerator and the denominator, we can rewrite the function as x plus 3 all over the quantity x plus 1. By substituting 1 to this new expression, we obtain 2. Although f is not defined at 1, the graph can verify that as we trace the curve from the left of 1 and from the right of 1, the y values approach 2, and therefore, the limit of f of x as x approaches 1 is equal to 2. This example illustrates that the limit of a function as x approaches c is not always equal to the function value. Let us try another example. Find the limit as x approaches 4 of the quantity 5x squared minus 2x minus 32 over the quantity x minus 4. Next, find the limit as x approaches 1/2 of the quantity 4x squared minus 4x plus 1 over the quantity 8x squared minus 2x minus 1. By substitution, we will obtain 0 in the numerator and 0 in the denominator. Thus, when we have an indeterminate value, we try to factor the numerator and the denominator, which in this case gives us a common factor of 2x minus 1. And after cancelling, we obtain a new expression of quantity 2x minus 1 all over 4x plus 1. If the algebraic technique is applied in substituting 1/2 to x, we obtain 0 as our limit. For our last example, let us find the limit as x approaches 0 of the quantity square root of x plus 1 minus 1 all over x. If we try to apply substitution to find the limit, this will result to the square root of 0 plus 1 minus 1 or equal to 0 and a denominator of 0. With this, does the limit exist? Can I factor and cancel? How will I rewrite the function? Since the expressions in the numerator and the denominator cannot be factored, we will try to apply the conjugate of one of the expressions by multiplying the function by the quantity square root of x plus 1 all over the same expression. This will result to a difference of 2 squares in the numerator with the square root of x plus 1 quantity squared being equal to the binomial x plus 1. In the denominator, we obtain x times the quantity square root of x plus 1 plus 1. Simplifying the numerator, we have x, and since x is also in the denominator, we can cancel and rewrite the original function as f of x equals 1 over the quantity square root of x plus 1 plus 1. With this new expression, substituting 0 to x will result to 1 over the square root of 0 plus 1 plus 1, or simply 1/2. And therefore, the limit of the original function as x approaches 0 equals 1/2. Let us now summarize what we have discussed. First, if a function f is a polynomial function, then the limit of f of x as x approaches c is simply equal to the function value f of c. Similarly, if f is a quotient of two functions such that f of c is defined, then its limit as x approaches c is also the function value f of c. If f of c is undefined, then the limit of f of x as x approaches c does not exist. However, if f of c will resolve to an indeterminate value, then you can rewrite the function either by factoring or using first a conjugate before factoring, canceling, and eventually substituting c to the new expression. For more examples, you may refer to the textbook and Learning Worksheet 1.2. Practice applying these techniques by answering the exercises in the textbook.